So we covered one part of the arithmetic building block lecture when we discussed the adder circuit, and we will cover the other part today, multiplier, and that's about it. You might be wondering, how about subtraction and division? You will see, it's coming up. I mean, not in a separate lecture, within this lecture only. And why are we not mentioning division and subtraction separately? You'll see that only adders and multipliers will suffice as arithmetic building blocks to give you the scope to do everything. So before we dive into circuits, let's do some really simple maths, like do multiplication. If I ask you to do that, forget about binary. Yes, I recognize these numbers are binary, but our multiplication has nothing to do with the numbers being binary. You see, we literally just take 1 and 0 and multiply them with each other, don't we? Just don't treat them like binary. Then, I mean, it becomes computer science. As long as you keep the word binary out, it's just like you just give it to your, I don't know, cousin or like a child next door maybe, and ask them to kind of compute this. I'm sure that any one of them will be able to do it, right? There is no electrical engineering associated with it. But as electrical engineers, we should be able to look at the approach that we take to multiply numbers and come up with ways to design circuits to achieve that. Making sense? Okay, so let's try to take some hints from this multiplication approach and see how we can shape it into a circuit. So we literally just take 1 and 0. Let me actually shape it in a truth table format. A, B, and this is the result. Say if 0, 0, 0, 1, 1, 0, 1, 1. Let's see. So you take 1 and 0 and you multiply them with each other, you get 0, right? So can I say 1 and 0 will give you 0? You take 1 and 1, you multiply them with each other, you get 1. So 1 and 1 should give you 1. And so on, right? You get 0 here, you get 0 here. I hope that makes sense. Does it make sense? Oh, wow. Okay. I mean, we were just multiplying numbers, but now we have something interesting right here in this truth table. Can anybody tell me which logic gate it actually represents? AND gate. Thank you. You see that? This is literally nothing but an AND gate. When both of these inputs are 1, only then you have 1. Other than that, you have 0. So it's nothing but an AND gate. So I can consider that when you're trying to multiply two binary numbers, just one bit at a time, you are essentially doing an AND operation with two inputs. AND operation with two inputs. Just keep that in mind. So in the first row, we typically just take the AND of all of these numbers with one of the multiplier bits. So this is multiplicand, this is the multiplier. You just take one bit from the multiplier and AND it with all the bits of the multiplicand. Is that a valid assumption? Okay. Without further ado, let me just get to the next slide and show you something there. So let's generalize this number in form of x0, x1, x2, x3, like bits of the multiplicand, and y0, y1, blah, 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 as the bits of the multiplier. Okay. So we take one bit of the multiplier and we will take the end of that bit with all the other bits of the multiplicand. Is that right? Can I do that? You see that you have y, which is just one bit of the multiplier, and we're doing, oh, let me just change the color. We're doing an AND operation with x0, AND operation with x1, AND operation with, all the bits of the multiplicand. These are AND gates. Any problem so far? Okay. You might be wondering about one thing. I don't know if you have noticed this. This is actually a NAND gate, not an AND gate. Okay. The reason, I mean, this is taken from a textbook. They love to confuse people. Anyways, so they took the inputs as inverted. So when you take an inverted input, the output will be inverted as well. So essentially, you're getting AND. And there are reasons, but forget about it. Just treat it like AND gates, okay? Then you should be fine. When you go to the next one, this is taken from another textbook. You see they're using the AND gate anyways. Am I making sense at all? These are AND gates. How do you know? There is no, circle on the top. So that's why this is an AND gate, which is the right thing, by the way. But this textbook didn't have this representation. So that's why I had to take it from other textbook. Okay. Anyways, let's get back to the previous discussion. So does this slide make sense to you guys? You see what we're doing here? The first stage of multiplication would be to take end of all of the bits of the multiplicand with one of the bit of the multiplier. Okay, that's the first stage. So let's get back to this simple slide again. So this is what we have done. It's taken end with of all the bits of the multiplicand with one bit of the multiplier. Then what? What do we do after that? I know that you guys have all done so at some point. You just cross out one space and start putting in the numbers towards left, meaning you start multiplying the next bit. Maybe this one, right? Like this. You do the exact same thing all over again, but you just cross out one section, one space, don't you? And what? And then you repeat the same procedure for the next one and the same procedure for the next one. Any problem at all? This all comes from simple mathematics. And we all know this, even kids know this, right? As long as you don't mention the word binary. Okay. Okay. I mean, you can always do this type of tricks. I mean, you could just bring your, I don't know, younger brother or cousin or someone, like goes to maybe 3rd grade or something. You can show off to your friend, hey, I teach my brother how to do binary stuff. You know, can you do this? I mean, your brother can do it. I mean, your friend might think, oh, your brother can do binary stuff. This is essentially a computer science, computer scientist already, but don't have to be. Anyways, binary is simple because you have just 1 and 0 and can have only 2 results, either 1 or 0. Anyways, the fact is we keep doing the same operation, AND operation, over and over again, and we get different rows of results. These rows, get used to this term. These rows are called partial products. So you have 1 partial product, 2 partial product, 3, 4 partial products. Okay. What determines the number of partial products? Can anybody tell me just by looking at these numbers, the multiplicand and multiplier? What determines the number of partial products? The bits of the multiplier. If you have 5 bits in the multiplier, you have 5 partial products rows. Any problem? Okay, so after that, what do you do? Let me stop here and ask you and see whether you can finish up this job. These spaces are crossed out. After that, what do we do? We just do addition. Yes, we just add these things up. Like we take 0, 1, 1, blah, 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 right? We just add them up. Can you figure out, as a computer engineer, the hardware that you'll need to carry out this? We have already figured out all these steps. Do AND operation, AND operation, AND operation, AND operation. So to get all of these rows, all you need to do would be AND operations, nothing else. Any problem? And you have to be mindful about one other thing. What is that? Spacing them out, right? You cannot just take an AND and put them anywhere. You have to space them out. Any problem? Okay. What else? We don't know how to space them out yet, but we know how to take the partial product, don't we? Are we all on the same page? We can all do partial product calculation. We don't yet know how to space them out. I'll show you. And one more thing that we have to do is to add everything, add all the numbers. Do you guys know how to do that add operation? Using what? Adders, the ones that you're designing. So you've already covered that. I hope that I don't have to go through that again because you already know how to design adders. But I hope you see that a multiplier is going to be way more complicated than a simple adder block, because multiplier will have a bunch of adders inside, inside of them. Okay, so having said that, let's get to the actual slide, which shows the multiplier. Okay, you guys ready for it? I know it looks complicated, but it will not be complicated if you pay attention. Okay, I would like to request your undivided attention for this. So please Take notice as I'm marking them because it will quickly get messy. Okay. So you have 4 bits, x0, x1, x2, x3, 4 bits in the multiplicand. And you have 3 bits, y0, y1, y2 in the multiplier. All right. So we should first take y0, x0, y0, x1, and so on. We should take AND of all of these bits. And you see we are doing that. So you have y0 and you're taking an AND with all of these x0, x1, x2, x3 bits. Any problem at all? So what are we getting? We are getting this first row of partial product. First row of partial product. What should we do next? Take the second row of partial product, right? Second row of partial product will deal with which one? If this is y0, we should deal with y1 next. Make sense? So let's do that. You see, you have y1. Forget about everything else. Just look at the red marked section. And you're taking an AND with x0, x1, x2, x3. And then what? Then y2. You're taking an AND with x0, x1, x2, x3. Then y3, x0, x1, x2, x3. Any problem at all? So all we're doing is calculating partial products. Are you guys all with me so far? I hope that's the case, okay? Now, so you have partial products right here. What should I do with those partial products? I should space them out, right? I should space the first partial product by 0 spaces, the second one by 1, third one by 2, the fourth one by 3. You see? You see the point? If you have 4 bits, which you had here, you need to have 3 spaces left in the final partial product, like 1 less of the number of bits. So that's exactly what we're doing here. You see, you have 1 partial product. Let me just use a different color here. This is the first partial product, and I leave 1 space for the next one and 1 space for the next one. Make sense? I literally just physically separate them in design. Does that make sense at all, or what? And don't worry, you don't have to draw this. You just have to understand this. That's it. You know, your exams are open book and open slides, right? You can always, oh, if I ask you to draw, you can, okay, this is how you draw it. That's not the point. Is there any question from the online folks?
Yeah. My question is, by physically spacing them, what do you mean? I'm a little bit confused here.
Yes, that's a good point. So by physical spacing, I mean by not connecting. Let me show you using a different color here. Maybe this one. So you see, I could have just taken this block and this block. See, you have 4 on the top, 4 exactly below this. I could have just, taken them right here and had them, I don't know how to explain. Let me just show it here. You have like 4 blocks. You could have just had the other 4 partial product blocks right here, right underneath each other, and the other 4 right here. Then this one fitting into the other one and the other one, and so on, right? Then we wouldn't have the effect of leaving spaces. But what we do is we actually take 4 blocks and then we put them like this. Basically, we just leave this space. We connect this with this one, the other one, like this. And the next one, we space it out even more. This way, we leave these 2 spots empty. Does that make sense? So that's what I mean by physically separating them.
And the function of the half header, the function of the half header that in those spaces we do not need. Okay. We do not need carry weight for this.
Yes. All right. So now after we've gotten all these partial products and we have managed to have all those spacing done. We have managed to leave the spaces behind already. Do you guys all agree with me? What is left? adding. We just need to add. Now let's work together to figure out what we need to do to add this. Okay. First of all, let's do the simple thing and then leave it for you guys. The very first bit does not need any addition. It will just directly go to the output. You guys all agree with me? Okay. The very first bit, this one does not, by the way, this Z0, Z1, Z2, Z3. These are the final bits of, and of course, Z4, Z5, Z6, Z7. These are the final bits of the multiplier output, right? You see, like if I add them up, you have, let me just actually add them up, okay? This is gonna be 0, this is gonna be 1, this is gonna be 1, and then this is gonna be 1, it's gonna be 0, 1 carried, 0, 1 carried, 1, 1 carried, and then 1, and then 1. Okay, so you see the point? So this is like Z0, Z1, Z2, Z3, Z4, Z5, Z6, Z7, Z8. Any problem? Okay, all right, that's what we mean by that. Now, so you have all those bits. Do you notice something? That this last partial product always show up. You see, that's what you are noticing here. Like all of these are coming from the last bit, and the other ones are coming from the previous stage. Am I making sense at all? Okay, all right, it's not unusual. Okay, so I've done the easiest part. The first output should directly go to Z0 without any adder. Are you not doing so here? There are no adders here at all. There is something interesting about the second output as well. Let's mark it out. The second stage, you need to just add 2 bits, not 3. Is there any carry in from the previous stage? Why not? Because we didn't even add anything. There will not be any carry. So this guy has 2 inputs, no carry at all. Remember half adder? We discussed this in the last lecture, that there are possibilities that you might not need any carry in at all, and you can simplify your circuit quite a lot, simplify going for a half adder, which has 2 inputs. You completely ignore the carry in. And you see, we can use a half adder for the second stage. And that's what you see here. So you have, this is half adder. All the other stuffs are full adder. This is also half adder, we'll see. Wherever there is an opportunity to use a half adder, we will use a half adder to save some transistors. Make sense? Okay. So the first one was easy. Second one is also easy. You are just adding the partial product of the first stage and the second stage, and you're using a half adder to do so. Any problem? Now that you have added, an adder will have a sum and a carry. Any problem? Folks, do you remember what I did here when I calculated? There was a carry generated at this stage, right? You see, when you add 1 and 1, you get 1, 0. So this 0 remains as the sum, and the 1 is carried to the next stage. You see the point? So the carry from the previous stage should be given to the next stage. Any problem so far? So that's exactly what we're doing here. The carry is given to the next stage. Wherever you have a carry, give it to the next stage as carry. So now this guy cannot be a half adder anymore. It has to be a full adder. It can take a carry, and then you have 1 input, the other input, 2 input, and a carry. And then you have some carry out, and so on, and so on. Any problem so far? Okay, let me show you one more thing. And here, let me just clear it up a little bit. So I guess we have covered these two. These two are done. What's left? Now, the third stage, you have 3 inputs. Can you use a regular adder to do so? Why not? Yes, thank you. We have designed adders with 2 inputs, not 3 inputs at a time. Yeah, the third input comes from carry. but that carry will come from the previous stage. It's not going to come from the same stage. So essentially, you are dealing with 4 inputs, 1 carry and 3 input. Can you do it in one stage? No. What should you do? You should first add these 2 numbers using an adder and add that sum of that adder to the next bit, and then you get your result. Am I making sense? Folks, are you guys confused or are you with me? Okay. Online folks? Actually, I told you that it's simple, but it's actually difficult to explain because it's so, zigzag of a figure. It's really difficult to keep track of stuff. But please let me know if you're confused. So you see, using this full adder, we are first adding the first 2 bits. Okay, and then we are using another adder which doesn't have any carry in. Right, there is nothing there to give it a carry in. So this is a half adder which takes in the sum of the first 2 addition and the other bit. So basically, we are adding this 2 again with that half adder. So without going into the details of it, as you see, all of these adders around the edges will be half adder because they don't have to rely on any carry in, no carry in at all. So that's why they can be half adder. We can save a lot of area by doing so. Any problem? Okay, let me show you one more thing. Let's go to the next level, even more complicated. Oh. Okay, now how about this one? Let's try to figure out how many adders we will need to compute this. You have 4 bits, and then there are carry-ins, by the way. There are carry-ins. So we don't really know how to handle that. So we have to take care of these 4 bits to add them up. First, we will add these 2 bits with 1 full adder. Any problem? And then what do you get here, by the way? By adding these 2, you get 1 bit. Maybe this is sum, S. Are you getting this? When you add these 2 things up, you get a sum bit, and carry will be given to the next stage. Okay, and then you add this sum with the next bit. You get another sum, maybe sum 2. You see the point? And then you add that sum with the next bit. You see what I mean by the next bit, right? So you have another adder and you have another adder. How many adders will you need to add 4 bits? 3 adders, right? And let's see. You have 1 adder, 2 adder, 3 adder. The last one is a half adder because there is nothing before it. I mean, nothing will happen even if you use full adders everywhere. I mean, you're just being wasteful. That's it. You're wasting a lot of transistors. That's it. Any problem? Anyways, you'll connect those transistors and set them to ground because no carry in, 0. Okay, does that make sense, folks? All I need to convey from this slide is to make you understand how this multiplier system is designed using the components that you already know. You already know how to design full adders. Now, take a moment to appreciate this. You guys are all working on your project with multiple transistors to make adders. Adder, right? If you have 28 transistors in your adder circuit, there will be 28 transistors sitting right here, and then 28, and then 28. Not 28 for half adder, less than that for half adder, but at least 28 for full adders. Can you appreciate how many transistors and how complicated this system will eventually be? That's kind of indicating VLSI, very large scale. It starts getting more complicated very quickly. And this is a simple multiplier. It's not even doing any, I mean, just imagine what you will have to do graphics design or something. Makes sense? But you don't have to start from the scratch. You see, you build upon everything somehow links to your inverter, CMOS inverter. Imagine that's where it all began. You started designing an inverter and then you started designing logic gates using the exact same principle as a CMOS inverter. Pull up network, pull down network. In the end, that's all that's happening underneath. So let me take a moment and ask you guys whether this block now makes sense to you. You don't have to memorize or anything, as long as you understand why we're doing it. And these are not just random connections. Oh, here goes an array. Oh, by the way, this multiplier is called an array multiplier because it looks like an array. I mean, the computer science folks can easily appreciate. I mean, whenever we structure them something like in rows and columns, it looks like an array. So that's why it's called an array multiplier. Okay. Now, moving to the next slide, some comments about this array multiplier stuff. Let me just use a different pen color. Which one? This one will be better. Yeah. It has many critical paths. By critical path, can anybody tell me what is the critical path of a ripple carry adder, the one that you're designing? The critical path. What do I mean by critical path? The path that has the highest delay. Yes, thank you. The carry path. So remember, maybe for 4-bit adder, you have two inputs. Sum, you have carry in, and then you have to provide a carry to get the sum out, right? So apparently your carry will have to go from here to here, here to here, and so on. So that's the biggest source of delay, right? That is the critical path that determines the overall delay of your system, adder system. For a multiplier, we have many critical paths. I mean, it's difficult to define the critical path, especially for an array multiplier. And here is an example for that. Critical path 1, 2, 1, and 2. See, if you start with a carry chain, the carry goes from here to here, and from here to here. See, you can count how many stages it will have to go through. If you take an alternative route, like maybe this one, you can have a different type of critical path. And the numbers will actually match. Let me actually count. You have to go from 1 stage, 2, 3, 4, 5, 6, 7 stages. You have to go through 7 stages to get to the output. Say the carry will have to go through 7 stages. Let's see the critical path 2. Critical path 2, right? Which is, let's just name it whatever we want. 1, 2, 3, 4, 5, 6, 7. You see, we have the exact same number of stages between these two critical paths. Any problem? It's like a maze or something. What is the problem with that? What is the problem with having multiple critical paths? In an adder block, know that there is just one critical path. We can do something to improve that path, to reduce the delay. Remember, somebody came up with an idea that, hey, we use inversion property to remove inverters at the output and reduce the delay. Remember, we talked about it, and that improved the performance. Why? Because you have just one critical path. If you somehow improve that, the performance improves. But for a multiplier, you have multiple critical paths. So it's difficult for you to optimize a multiplier than to optimize an adder. Am I making sense? But remember, anything that you do in the adder level directly benefits the multiplier, because the multipliers will have a bunch of adders. If the adders are improved, multiplier will automatically improve. So we definitely try to make sure that the adders are as optimum as possible. Now, my question is, folks, remember, people went through some computer science stuff to figure out inversion property, duality, self-duality, something like that, right? To save a couple of transistors, 2 inverters. And I convinced you that, tried to convince you that's impactful. Hey man, these guys solved a big issue by getting rid of 2 transistors. And it's like, and we are sending rockets to the moon, huh? And these guys removed 2 transistors. I mean, it sounds like that, but it will quickly make a lot of sense when you think you're removing 2 transistors from all of these blocks. Now you suddenly have like 50 transistors. You see, even that's not shooting to the moon, but it's getting there. So things quickly get more impactful as you move up the chain to the system level, right? So any improvement in a smaller system will directly benefit the larger systems. Okay, now I hope you guys have already gotten used to this fact that we will start with a problem. That, hey, here is the problem. and then somebody will propose a solution. That's how research works. Okay, and anything that these guys do in research somehow trickle down to the textbooks 10 years after that. Okay, so textbooks, 10 years, the textbooks used to be 10 years behind the research frontier. Now they're probably 25 years behind. I don't know. Because the fields are so aggressive right now in terms of research. Research is accelerating. Why? You need to ask. At some point, people didn't have simulation tools. They used to do everything manually, hand calculation. People used to calculate the value of pi, the digits of pi after 3.1416 manually using geometry, basically at some point. And then computers came. Now you have supercomputers. You can literally do a person's lifetime of work in like few seconds, to be honest. I'm not kidding. Seriously. I mean, I've watched a documentary of how people used to, there was a mathematician who was really bright and everything. His life's work was to calculate maybe thousands of digits of pi after the decimal point, right? And that was really, really difficult at the time to do using a geometry-based approach. And then Newton came, and Newton proposed a binomial theorem, and used the binomial theorem to calculate pi in a more efficient way. And suddenly things started becoming more, easier. And people used to think, see, we radically changed the world. And then the computers came in and said, okay, so now you're talking in terms of thousands, let's talk in terms of millions of points or billions of points or whatnot. Anyways, the fact is, the capability to discover stuff is accelerating. More importantly, now when people go for grad school, many of you will probably go to grad school. The first stage towards doing something is to see what else has been done. Okay? We do literature review. We see what other people have done and where is the bottleneck, and can you do something to solve that or get around that somehow. Now you can easily Google stuff. Hey, problem with multipliers, websites, YouTube video, you have everything. You can do maybe like 10 years worth of background study in an hour, maybe. 20 years ago, even 30 years ago, people used to go to the library. They used to bring out books, read through books, you see, to figure out what else has been done, but not anymore. So that's why the discovery has been accelerated. Sorry for taking the tangent, but I wanted to just add some perspective as to how people, I used to think about it all the time when I was a student. How did somebody come up with this idea? Was it random? In a day, that person just thought about a solution? Probably not. They have to go through a lot of literature review and whatnot. So it all comes down to the difference between the first approach that we learned, this one, and the next approach that we are going to learn right now. I hope you guys are not too bored. Are you? Yeah. Okay. See, in this approach, we didn't do anything fancy. It was all plain vanilla. Add, provide the sum, send the carry to the next level. Add, provide the sum, send the carry to the next level. Okay. The carry was given to the block, the neighboring block in the same row or something like that. Somebody noticed something interesting with numbers. They figured that, hey, if you provide the carry to this guy, please pay attention to this. Okay, this is a little bit difficult to explain maybe. See, maybe let's imagine you have a carry right here in this block. You have a carry right here. Okay, you have 0 and 1 as carry. Does it matter who you add this carry to? Can you tell me? Does that matter? As long as you add it to something on that column, it doesn't really matter who you are adding it to, right? You agree that? Okay. For example, imagine you had a carry here. You don't here for this particular example, but if you had say 1 and 1 here, you would have generated a carry. It doesn't matter whether you add that carry to this number or the other number. Doesn't matter. Normally, we just give it to the next neighbor exactly along the same row. And that's how this design was made. This is how this design was made. Give the carry to the neighbor exactly along the same row. That's natural. However, they figured that if you somehow provide the carry, not directly to the neighbor, but to the next stage, there is a benefit. I'll tell you the benefit later. But can you see that we can do it without changing the total result? Do you appreciate the fact or not? We can provide the carry. Instead of providing it to the next neighbor, you can provide it to the next neighbor in the next row, in fact. Make sense? Okay. As long as you agree that you can do it, now I will show you how that helps. It actually brings down the number of critical paths to 1. Let me show you. This chain is now going to be the critical path. 1, 2, 3, 4, 5, 6 stages. And any other stage that you see, there is no chain. See, you don't go from here to the left. Not at all. There's nothing going from right to the left. You're just trickling down from top to bottom, right? So this, obviously, there are challenges with this approach as well. There are, some other issues, but they proposed doing so to save the problem with critical path. Okay. All right. This is called carry save multiplier. Why carry save? They justified the fact that, hey, rather than providing the carry to the next level directly, we are saving it for the next row. And that's how they just came up with the name. But apart from that, it doesn't, mean much. By the way, I just wanted to show you, this is exactly the same circuit as this one. This is how it is laid out in actual chips. We don't really, have interconnects that bend. Interconnects don't bend, right? And the concern is, if you design a multiplier in this way, remember Tushar asked me this question: what do you mean by physical separation of the blocks? I meant that you kind of space them out and don't connect them with each other. That raises a concern. Are you not wasting this much area within the chip? And you're literally wasting this much area, right? Aren't you? Wow, that's the waste. But we don't do that. So the next slide was meant to show you that. No matter what type of connection you use, you always go for this rectangular shape. Row and column. They're all aligned with each other. But you connect them, you just change the interconnects. You just play with the interconnects. You don't have a vacant space like this. So don't worry. This is only to help you understand. Same here. This is only to help you understand. We don't waste this area at all. We just, make them rectangular to make sure we don't waste anything. Okay. There is nothing else new about it. It's exactly the same as what we have discussed. Just wanted to show you how things are laid out. Okay. Now, Wallace tree multiplier. Another interesting concept. You see, we are not going through any circuits at all. Okay, we are just going through the concepts, because the circuits will essentially be the same. You just change some connections, you just add something to the existing circuit. That's it. Okay. By the way, folks, if I give you a homework, which I will not, by the way, so don't worry. If I give you a homework that, hey, come up with the schematic of a 4-bit array multiplier, say, for example, right? 4 by 4-bit array multiplier. Schematic, you need to show me transistors. Can you not do it simply by looking at this slide? Just convert all of these AND gates with 2 NMOSes, 2 PMOSes, all of this half adders, full adders. You have a poster, maybe, right? Something like that. But but you can, right? If you wanted to. But imagine in Cadence, that will be difficult for you guys to do, like draw and everything, right? But in Cadence, you have used symbols, haven't you? You just make one block for the adder, the way you have done, right? You have made NAND gate, but AND gates essentially similar. You can use your adder circuit that you're designing for your project, and then copy and paste. Done. You have your multiplier block. You can easily test it out at home if you're curious, which you probably are not about multipliers. Who cares about multipliers at this stage, right? Anyways, but keep this in mind. I hope you have appreciated this already, that everything that we are learning, they are building block for the next big thing and building block for the next big thing. If I told you that these multipliers are building blocks for AI training, that would probably make you excited. Wow, machine learning accelerators. Machine learning accelerators are nothing but dot product engine, and dot products are product multiply. Product means multiplication. Basically, you're multiplying matrices. That's it, and you need multipliers to do so. Okay, now it's fancy. Oh wow, machine learning accelerators. I see. I could have had a lecture on machine learning accelerator design on VLSI, but essentially keep the same slides. Anyways, Wallace tree multiplier concept. This is a really nice concept that I like. That's why I wanted to explain it quickly. Let's see. One more thing that we realize from number theory. Let's take a moment and look at these numbers. You guys ready for it? Okay. See, if I just take a notice as these numbers, 1, 0, 1. If I push this one up and this 0 here and this one here, basically just shift all these 3 numbers up, all these 2 numbers up, and this one up. You see, what will I have here? Let me actually do it. 1, 0, 1, and you don't have anything here. You have 0, 0. You don't have anything here. This is 1, and you have 1 here. You don't have anything. Let me just use black markings to cross them out, or maybe something else. Sorry, maybe something else to cross them out. Do you see that it kind of looks like a pyramid right now? You see that? Kind of looks like a pyramid. Does it matter if this one is here or here? Does it matter at all? Eventually, you'll just add them up. Doesn't matter. You are anyways adding them up, as long as they're in the same column. So if I change this one and bring it here, it will not change anything to the result, will it? If I take this one from here and just put it here and add a 0, maybe it's not going to change anything at all. Okay, so that's what people realized, and they started designing circuits using that approach. Let me show you. So these dots are the numbers. I hope you can see this, right? This is partial product. These are the partial products, and these are the spaces that we crossed out. Does that make sense? Instead of using actual digits, we're just using dots to represent. Yeah. Now, you basically just push them up like this, and you come up with this pyramid shape. Any problem at all? You can try it out with pencil at home and kind of erase out the stuff that you have moved. And you'll see you can easily come from partial products to the first stage. Are you guys with me so far? Any problem? Why are we converting this to a pyramid like this? Let me show you. Given a chance to use a full adder versus half adder, which one would you prefer? Half adders. If we can somehow increase the number of half adders in the design, that will save a lot of area. So their idea was to redesign the numbers in a way that the usage of half adders increase and usage of full adders reduce. Any problem? Let's see. We don't care about this. We don't care about this. These are all simple. You already use a half adder, right? Let's start with the ones that are more problematic, the ones that have more bits. We'll worry about the other things later. So here, when you see these 2 bits coupled together, you use a half adder. Basically, you use a half adder to add them. So this is the first stage. Use a half adder and half adder. Any problem? I mean, we are just getting there. We're just getting started. But all I'm telling you is what they proposed. They proposed that use a half adder to reduce the ones with the most number of bits. All right. So let's see how we. I mean, what we get out of it. We start with this 2 addition. When you add these 2 bits, how many bits will you get? Can anybody tell me? When you add 2 bits, you get a sum and a carry. Okay, so you get a sum, meaning instead of these 2 bits, you have 1 bit. Any problem? Tell me. So instead of these 2 bits, let me just add a different bit here. You have 1 bit. So you have 3 right now, don't you? And what happens to the carry? Where will it go? To the right or to the left? To the left. Okay. So I will add the carry. Let me use a different color for carry. The carry will be here. Doesn't matter. These are all bits. These are all, binary numbers. This carry will come here. But what happens to the numbers that you're adding? These two. How many bits will you get out of it? 1 sum and 1 carry. So can I say that these guys will go away? You get a sum bit and a carry bit here. That carry will go to the left. Any problem? Tell me. So now help me out figuring out how many bits we have. How many bits do we have here? 3. So we have 3 bits. How many bits do you have in number 4 position? 3, and number 5, 3. We have 3 bits here. So we have kind of equalized these levels. You see that? Any problem so far, folks? Okay. And what type of adders have we used? Half adders. We didn't take into account. You see the point? Okay. So we have used an half adder here. Now, for this point, when you see 3 bits lumped together, you consider them to be full adders. So at this point, we use full adders. Full adders. Full adders. Am I making sense at all? And with these full adders, how many bits will you get? Like when you have 3 inputs, maybe A, B, and carry in. How many bits will you get? You get a sum and a carry. Okay, let's start with this half adder. Okay, please listen to me. If you have confusion, please stop me and ask questions. Okay, let's take a look at this guy and correspond that this is number 2, number 2. When you add these 2 bits, you get a sum. This sum remains here. See, this is the sum. And what happens to the carry? The carry goes to the next level. You see that? See that? And by the way, you're already adding this thing up. By adding these 3 bits, how many will you get? 1. Instead of these 3 bits, you'll get 1 bit. So how many will be left at number 3? 2 bits. And the carry bit will be given to the next stage. And then so on. These 3 bits will come down to 1, and you get 1 more. And this 3 will come down to 1, you get 1 more. So you have 2 bits in all these positions. Am I making sense at all? Okay. So eventually you are left with all 2 bits addition, and all of these will be half adders. Again, you don't have to be too serious about it. If you want me to go over this in detail and maybe show you some examples, I'll be happy to. Maybe we could do it offline. But I just wanted to give you some sense as to what type of approaches people have taken to improve their circuit performance. Okay, this is there is no circuit involved here, as you see. The innovation is not in the circuit. The innovation is where? In number theory. So people have, reshaped the way we add stuff. That's it. Why are you so silent? Is this confusing? I know it could be a little bit confusing, but I try to guide you through the process, but you don't have to worry too much about it. That's what I'm saying. Okay. So essentially, you come up with a number pyramid and reduce the number pyramid gradually using an algorithm that these guys proposed. And then you reduce the number of total full adder and half adder. And by the way, the reason why you don't have to be too serious about it is because this is not even the cutting edge. Okay, so people have come up with more ingenious techniques already. They're not waiting for us to, oh wow, let's keep using this. They have come up with, the researchers need something to publish, right? You always, this has some problem, figure out the problem. But that's so perfect. Nothing can be perfect. Come up with something. Okay, so they come up with ways to further improve it. Anyways, let's move to a different discussion. Shifter. And you see, by the way, that ends our discussion on multipliers. That's it. Okay, so shifter. And this will also show you one other keyword right here. You see, divide. What does that mean? So basically, this shifter is an interesting circuit that helps you multiply as well as divide. And here is how. Let me show you. Imagine you have a number 001. Okay, if you shift it by one space, in computer science, when you shift, you just fill the previous digit with 0. Am I making sense? I mean, the digit at the very edge with 0, right? So we can convert this 001 to 010 by shifting by 1 bit. And as you know, this is just 1 in decimal, and this is 2 in decimal. Are we not multiplying the first number by 2 by shifting it by 1 bit? See that? Okay, let's do it one more time. 100. And in decimal, this is 4. Are we not multiplying the second number by 2 by shifting it by 1 more bit? So anytime you shift a digit, shift a binary number to the left by 1 bit, you multiply it by 2. And by the way, you can just do the opposite, shift it to the right. Go from 100 to 010 and 001. It's as if you're dividing it by 2. So depending on whether you are shifting it to the left or shifting it to the right, you can use it as a multiplier or as an adder. So this is a form of multiplier which multiplies by different. By the way, if you shift it by 1 space, that's multiplying by 2. If you shift it by 2 space or 3 space or 4 space, that represents multiplying by something else, by the way, right? And I don't want to get to the detail of this, number theory and computer science. I just want to show you the circuit. And there are ways. You can just tell me, how many bits do you want to shift it by? 2 bits? 3 bits? We will implement that in circuit. How about that? And that's a really powerful way to implement a multiplier and a divider as well, right? Let's do that. This is really simple approach to design this shifter. Are you guys with me so far? Okay. AI and AI minus 1, they represent the bits of number, maybe like 101. This could be AI minus 1. This could be AI. Like ith bit and I minus 1th bit, like the previous bit. Okay. So don't worry about these numbers. AI. This is the next bit. This is the previous bit. Okay. So when I write down these numbers, AI minus 1 will be on the right. AI will be on the left. If I want to go for shifting to the left, remember, let me ask you a question. If I shift to the left, can I say that this, by the way, the next one will be AI plus 1. Do you agree? And the next one will be AI plus 2. And so on. If I shift to the left, AI will be AI minus 1. Do you agree? And AI plus 1 will be what? AI plus 1 will be what? No. AI. Shift to the left. Make sense? Does not make sense? Okay, let me just clear it up a little bit again. I'm shifting to the left, okay? So AI minus 1 should go to AI. So this should happen. And AI should go to AI plus 1, and so on. If I shift to the right, it should be exactly the opposite. Any problem? Okay, now let's see. You have AI minus 1 and AI. And this is the shifted bit, by the way, shifted bit. If I shift to the left, this AI minus 1 should go to BI or BI plus 1. Which one should it go to? Shift to the left. BI could be the next AI, by the way, right? That's what I'm saying. Can anybody tell me? Yes, thank you. If I shift to the left, following this route, AI minus 1 should go to this one. And let's see whether it does so. Let's see. Let's try to figure it out. Yep. AI minus 1 is coming here. And I'm trying to shift left. Okay, first let me explain no operation. That's going to be easier. When you have no operation activated, this transistor is active. When I say a transistor is active, this is a transistor that is driven by no operation, right? Do you see that? This transistor is active, means what? This directly goes as input to this buffer. Any problem? Any problem? And by the way, this looks like an inverter, but it is not. It could have been an inverter if you had this not in front of it. It's called a buffer. Why? When you have multiple inverters, even number of inverters connected in series, that's called a buffer because it doesn't invert. Okay. Why do we still use it? It helps with noise suppression. It helps with restoration of the signal. Signal degradation, remember, inverters can resolve that. And that's why we have buffer, multiple inverters, even numbers. They don't invert, they just restore the signals, okay? So this AI will be directly connected to this buffer, and you have BIM minus 1 equals AMI minus 1. Yes?
Your question with the buffers, usually just two inverters? Or...
No, that's a good question. Typically, 2 will be the minimum, and we would love to have 2. Sometimes, in some applications, we often have to use more, right? But if nothing is specified, always assume that 2 inverters, okay? Because that's going to be the most area efficient way. And there are scenarios in circuit design where we have to use more inverters to create a buffer. Okay, depends on the current rating of the next circuit. Again, that's going too much into a different direction. But that's a great question, Bill. Okay, make sense? Okay, when you have no operation connected here, this AI will directly go to BI. So you see, did you shift anything? Did you do any operation? No. So that's why no operation. So you have a choice to not operate at all. Okay, I wish we had choices like this everywhere in life. Like you have an exam, you turn on no operation, nothing else. Anyways, okay, so AI minus 1. Let's see what happens when you have left shift turned on. Okay, let's start with AI. No operation is off, so this transistor is off. Can you go through this line anymore? No. Okay, by the way, this is connected to, let me show you. This is also connected to this line. But your right shift is off. So can it go through this line at all? No. It's a problem, right? But let's see what happens to the other guy. AI minus 1 is connected to this line, and this left shift is on. So now this guy will be connected to BI directly. Do you see the point? This left is on. So this AI minus 1 will find a way to go all the way to this buffer. So BI will be AI minus 1. Am I making sense? What happens to AI? It will go to the next stage. Actually, there are stages on the top and stages below it, which I'm not showing here. It's like a slice of the 2-bit section. Am I making sense? And by the way, you could do exactly the same thing using the right shifting option. Let's see. Okay, let's see. When you have right shift activated, so this guy is on. So you have this AI coming up to this point and then going through this channel all the way up to BI minus 1. So you see, you are taking AI and giving it to the previous stage. That means you are right shifting. You can do left shifting, you do right shifting, you can do no shifting. It's up to you. Any problem so far, folks? Okay, so by doing left shifting, you multiply, right shifting, you divide. Interesting circuit, simpler, and looks really, easier to implement. By the way, this is another example of a shifter, but this one is called a barrel shifter. This shifter allows you to shift a bit with multiple digits, meaning you can shift it by a 1 bit, like we have done before. You could do it by 2 bits, 3 bits, and so on. Let me show you how. Maybe just illustrate one example. Guys, ready for it? Any problem? Okay. You have A0, A1, A2, A3. How many bits? 4 bits. You need to shift them to B0, B1, B2, B3. Okay. Let me shift it by 0 bit first. 0 bit. I will not shift it. It's like the no operation. Let's start with it. A0. Please pay attention as I'm explaining. Otherwise, it will be messy very soon. When you enable shift 0, this transistor is on. So you have A0 connected directly to B0. Any problem? Same thing. This shift 0 is also connected here. You see the point? Shift 0 is also connected to this transistor. So this transistor will also be on. And this is connected to what? A1. A1 will be connected to B1. So you have A1 equal B1. So as you can see, when you enable shift 0, all of this will just directly go to the output. Done. So no shifting at all. Any problem? I mean, if you don't have to memorize. When you forget, you can just do exactly what I'm doing. Taking an example and going through the chain. Okay, let's do the other thing. Let's shift it by 1 bit. Enable this shift 1. Ready for it? Let's shift it by 1 bit. This transistor is on. Let's see what it is connected to. This guy is connected to A1. Do you see that? You see that? This A1 will go to B0. Any problem? Let's use a different color now. This shift 1 is also connected to this transistor. So this transistor will also be activated. Any problem? So this transistor is connected to what? A2. A2 will go to B1. Do you guys see this? You see that? And what happens to this one? So it will be A3 and so on. Any problem? So we are shifting by a bit. See, A1 is going to the 0th position. 2 is going to first position. 3 is going to second position. So it's shifting to the what? Right. This is a right shifter example. You can always implement the other one. Folks with me so far? Any problem? Okay. You want to see 2-bit shifting? Let's go. Shift by 2 bits. This is the only example in this lecture which will show you that. Okay. Shift by 2 bits. Ready for it? You enable shift by 2 bits. This transistor is on. Okay. Let's see who it is connected to. A2. You see that? This A2 will be connected directly to B0. How many bits have we shifted it by? A2 going, instead of going to B1, it is going to B0. So you have shifted it by 2 bits. Make sense? Okay, let's see who else it is it driving. It is connected to this transistor, which will also be activated. And let's see, this is connected to this guy, A3. A3 will come all the way down, go through this transistor to B1. So see, you're going from 3 to 1. So 2 bits. This is a really nice and simple way. There's nothing fancy about it. If you think about it, right? It's all about how you connect. Interconnects are the key here, the metal lines. Any problem? Let me upload some examples, Peyton, if that is okay. Okay, let me just use some numbers and maybe just copy and paste it multiple times, and I'll work it out using real bit 1001, and that will probably help you understand this better. And by the way, this is just a layout of this. There is no need to go through this. I just wanted to show you that this is how it looks. You have a bunch of metal wires connecting. Nothing but exactly this circuit. And these are the inverters that you know, buffer. 1 inverter, 2 inverter, 2 inverter buffer. Remember about this barrel shifter? And I uploaded a detailed description. I worked out the details there. Let me show you as well, so that you know what to expect. So this is the file which I uploaded. So I started with 1. Let me see if 1 bit shifting. Sorry, 0 bit shifting, 1 bit shifting, 2 bit shifting, and 3 bit shifting, as you see, right? We have explored all the capabilities of this circuit. So it turns out the circuit that the textbook guys provided, it implemented a different, very specific type of shifting operation. As you see, they replaced the MSB with the MSB as well, instead of replacing it with 0. something like that. Okay, that's why the circuit was a little bit weird along this side, along the column. But I hope when you go through this, it will make sense. Okay, but if it doesn't, please let me know. I'll be happy to go over it again. Okay, now let's get back to the lecture. We just have one slide left. Remember this very last slide. We have had a separate lecture on adders. We have had a separate lecture on multiplier. How about division and subtraction? And I just told you that shifter can divide, right? A shifter can multiply or divide. And turns out shifter can be a better solution to implementing a regular multiplier using the approaches that we have learned so far, right? Am I making sense at all? Remember this lecture, we had multiplier which had adders inside of them. So we talked about how many transistors you will end up getting simply by implementing that, right? Then this shifter, appears to be a really nice solution, but there are limitations. I mean, don't get too excited so soon. Shifter can only multiply with certain amounts, right? It can multiply with 2, 4, or something like that. You cannot have any arbitrary multiplication done with a shifter. The shifter is designed to provide a specific type of multiplication by factor of 2, factor of 4, factor of 6, depending on how many bits you're shifting. You cannot have a multiplication by 13, for example, abruptly from a given circuit. Okay, am I making sense? But if you are just dealing with a specific type of multiplication, then a shifter is a great option of doing so. Now, just to show you how easy it is for you to implement a subtractor right now, let me just ask you one thing. 1101, a binary number, 1001. I want to subtract this binary number from the first number. Okay, let's name them A and B. I want to subtract B from A. So instead of writing A minus B, can I write A plus, by the way, both of these are binary numbers. Can I write 2's complement of B? How many of you guys know this? Computer science. Okay, so subtraction is nothing but 2's complement addition. And how can I get 2's complement? I can just always take 1's complement of B and then add 1 to it, right? 2's complement is easy to get. Just take a binary number, take its 1's complement and add 1 to it. If you guys don't remember this, now you know. Now, my question is, okay, how do you take 1's complement? Actually, it's super easy to do. Just take any number, invert the digits, change 1 to 0 and 0 to 1. 1's complement. Right? I hope you guys remember that. Can you guys tell me about a circuit that changes 1 to 0 and 0 to 1? Thank you. Thank you. Yes, you guys know this already. So let's go to the next slide. So you are trying to subtract input 2 from input 1. So just take, yeah, I mean, that's okay. I don't know, maybe if you see me shooting spider webs sometimes in the future, this guy's to blame. Anyways, subtracting input 2 from input 1. And all we are doing is taking 1's complement of input 2 by using this inverter. And then you see, you are just let's just get back to this. You add A with 1's complement of B and 1. You just add these 3 numbers, right? So I will add A and B. Let me just use this adder block right here. You just provide A right away, and then you provide 1's complement of B. What else do you need? 1. You just need to add a 1. You can always use this carry in to be 1, and there you go. This simple adder will now act like a subtractor. Make sense? So that's what you see. This carry in being 1 is only there to convert this 1's complement to a 2's complement. Done. And then you get subtraction. See, that's why you don't have a separate lecture on subtractor. Okay, it's applied. Okay. And interestingly, you can have other circuits like a comparator that compares whether between two inputs, which one is greater? Okay, let me show you how. Can you guys see that this part and this part are actually identical? Basically, I'm going to use a subtractor, and I'll just use another CMOS inverter to compare whether input 1 was greater than input 2 or not. Make sense? Okay, let me show. Basically, a subtractor provides you a number that can be positive or negative. And especially the computer science folks know that there is a sign bit that we can always use, right? The leftmost bit. If you have a 0 in the sign bit, that represents positive number. For example, 0, 1, 1 or 1, 1, 1. Basically, if this is a sign bit, this represents positive 3, this represents negative 3, right? In binary. Again, I'm not going to on everything, just to remind you that the sign bit will either be 0 or 1, depending on whether a number is positive or negative. 0 for positive, 1 for negative. Let me ask you something. If input 1 is greater than input 2, what's going to be the sign bit at this point? The sign bit, only the sign bit. 0 or 1. Meaning, if input 1 is greater than input 2, then by subtracting input 2 from input 1, you get a positive number, don't you?
0.
Yes, thank you. So if you actually have input 1 greater than input 2, then the sign bit will be 0. And when you have 0 here and you use an inverter, it will give you a high output, like 1. So whenever the inverter is activated, by getting activated, we mean whenever it provides you a high output, it shows that input 1 was greater than input 2. And if the inverter gives you 0, that means the sign bit was actually 1. That means input 1 was less than input 2. Am I making sense at all? If you are wondering what if they're equal, a comparator, I mean, this particular simple comparator can only compare whether something is greater or less. And it will never be able to handle whether these two inputs are equal, because there will always be asymmetry. There is always be variation. We can never perfectly check whether something is equal to something else using this simple circuit, by the way. Okay? This is only here to show you how easily you can make other systems using the systems that you already know. Make sense? That's why we didn't show the circuit detail or anything. It's all the same, just the approach is different. So that concludes our arithmetic operation lecture.